Hello, everyone, and welcome to this webinar. My name is Michael Evangelista, and I will be your moderator for today. Just few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want in the chat box, and those questions will be answered by our panelists in a Q&A segment. The recording and certificate of this webinar will be sent out in 2 days' time for those who completed the webinar. And our topic for today is about diagnostic insulation resistance testing, and it was presented by our expert from the US, Jeff Johet. So without any further ado, let's start the webinar, Grace.
Hi, everyone. Thank you for joining us for another webinar today. Today's webinar is Diagnostic Insulation Resistance Testing with Jeff Jowett. I am Meredith Kenton, Megger's Digital Marketing Specialist. Again, if you have any questions about webinars in general, feel free to reach out to me via email or phone. If you have questions throughout the presentation, we ask that you use the panel on the right-hand side of your screen and you just submit your questions there. At the end of the presentation, I will ask Jeff as many questions as possible given the time limit. If your question isn't answered, don't worry, we will get you an answer via email in the days following the presentation. And with that, today's presenter is Jeff Jowett. He is our Senior Applications Engineer. If you have specific insulation resistance testing questions that you weren't able to ask during the presentation, feel free to reach out to Jeff directly. And I'll give it over to you, Jeff.
Yes, good morning, everyone. And thank you for attending our webinar. This is a follow-up to the one we did a week ago, which was fundamentals of insulation, how it's structured, how the structure breaks down, how you can have different problems develop with it, and fundamentally how you can test it to head off the problems or fix the problems. Now, this afternoon or this morning, depending on where you are, we're going to look at a little more detail of the procedures and the different types of testing procedures and what you get distinctly out of each different one, as well as some general information. And Meredith did mention you're welcome to, my phone number was up there, and you're welcome to call me with any questions at any time. Glad to talk to you. Okay, next. So look at some of the equipment here. This is basically just a reminder. Insulation testing pertains to any electrical equipment, large and small. These are just a couple typical examples. Next. And we're going to talk a lot about diagnostic insulation testing. The idea being here mainly that you can get more information by using a tester more fully, as opposed to just getting a single reading and then trying to go from there. So we're going to try to elaborate on that a bit. And with diagnostic testing, one of the things that you can do is arrange your work schedule in a more effective manner, where you're not just automatically testing at a certain time. You may not need to do that. You can be more effective with your work time and developing a diagnostic testing schedule. And we're going to take a look at that as we go along. Next. And a little quick review of what we talked about last week. These are basically the things that degrade the insulation on your equipment. Electrical stresses from voltage spikes and current surges, mechanical from vibration and dragging cables and things like that. And then, of course, all the corrosive attacks from things that are in your environment. And the last one there, environmental contamination, more than anything else, that's moisture. Okay, next. So these problems feed on each other. And so, for instance, you have at time of manufacture, you can have a tiny void somewhere in the insulating material. And during operation, that's going to arc across, that's going to keep arcing. And eventually you start to get a burn track. And then the burn track attracts more leakage current. And then over time, that breaks through the ground and takes your equipment out. So just keep in mind that these these destructive factors feed on each other and tend to make the problem worse and worse over time. But by taking measurements, you can get an idea where you are on that time scale, and you can adjust your work schedule accordingly. And many times you can head off uh, problems that, if left neglected, would eventually break down. Next. These are the things you're trying to, the main problems that you're trying to avoid with having good insulation and insulation testing. Of course, the main one would be electric shock. Insulation breaks down, you get a voltage gradient across a metal frame of a piece of equipment, and you do not want to become the path to ground. There's also a lot of fires that are induced in this manner. Don't rely on your circuit breakers to protect you. Yes, they do, but not in every single instance. With equipment, you have relatively narrow space between the electrical circuitry and the surrounding case that can get filled up with dirt and other corrosive chemicals and so forth. And then over time, the temperature builds up in a tight space and you get spontaneous combustion. And that's where a lot of your electrical fires, that's how they originate. You can also prolong the useful life of equipment by maintaining it rather than just letting it run to breakdown. And then finally, you can avoid unscheduled breakdown, unscheduled downtime, which in some industries like railroad, for instance, is simply unacceptable. Next. And the main thing we're going to talk about a lot here today is the nature of insulation breakdown. Modern materials are huge organic polymers that are all linked together. And as the insulation ages, those polymers start to break down. You get what is called polarization. They have charges across the polymer, and this leads to electrical charges developing in the insulation, which in turn your leakage current and your problems tend to exploit and break them down. And we'll be looking at the structure of insulation as we go through this presentation. Next. So the two main types of tests are go and no-go testing and diagnostic testing. And there's a substantial difference between these two types of tests. And it might be a good idea at the start of a testing procedure to just think about, where are you with respect to these two alternatives. Go, no-go obviously is you're just looking to see whether something's good or bad. You're doing troubleshooting when there's been a problem has developed. You're trying to find, is a motor who kicked out the breakers, is it an electrical problem, or is it a problem with the bearings? And so you make a quick insulation test, and that's your go, no-go type testing. Or are you just trying to meet a standard? Somebody has imposed on you that you want your particular piece of equipment should have X amount of resistance, and so you're just trying to check to see if you meet your standard. So with that type of testing, it's relatively simple, and you don't necessarily need a high-end tester. Average testers go to maybe a couple of gigohms in measurement range, and nothing is bad when it's up in the gigohm range. So if that's all you're ever going to do, you can go with a relatively simple and relatively inexpensive tester. But for diagnostic testing, there you're trying to get an idea of predictive maintenance. Where is your equipment on its life cycle? Is it like, remember the insulation resistance readings work like a car odometer, but in reverse. They start out real high. Brand new equipment is likely to be off the scale of your tester, but over time, the resistance gradually drifts down. And so it's like a car odometer in reverse. You want to see, where am I on the life cycle of this equipment? If you're up in the teraohm range, you don't have anything to worry about. If you're getting down in the low megohms, then you have to start taking preventive procedures. Next. And so we're going to look at a number of different types of tests. And remember, for instance, this is like going to the doctor. He doesn't just take your temperature and then give you a diagnosis. He does several different tests because different tests are looking at different things and different potential problems. Insulation testing is the same thing. You have different types of tests and they look at the insulation in different ways. And so we're going to review that today, and we're going to see how different test procedures look at different potential problems. Okay, next. These are some of the tests that we're going to look at. To fully discuss them, of course, would take a lot longer than an hour, so we're only going to review them, but we do want to give you an appreciation for what the different tests do. A lot of them you can kind of do them by yourself manually by the way you manipulate your tester. But on the other hand, if you have a high-end tester, a lot of these are already programmed in there and you just select them. So we'll give you some idea of how to make the most use out of that. Next. All right, currents. This, we'll start with, I think we mentioned this last week. We're going to review it again this week. This is why you see different numbers when you start a test. And this is very confusing to people, operators who are have never been given any review or any training or anything of that sort. This is why on an insulation tester, your readings change over time. And so you start a test and you look at your display and the readings are jumping all over the place, or they seem to be. Actually, they should be rising steadily. But this is very confusing to somebody who's never been given any training on it. And the reason for it is insulation draws different currents, capacitance, absorption, and conduction or leakage. All these currents are being measured at once, and this is what you're seeing up on your display, the net effect of all these different currents. Okay, next. So this is what they do. Your capacitive charging current is in the capacitance of the test item, and it's in the design. It's there. It doesn't vary appreciably. There's nothing you need to worry about. But a big motor winding, for instance, has a lot of capacitance. And so that will charge up at the beginning of your test. But it occurs quickly because it's in metal, which is a good conductor. So that's why on your old analog testers, the pointer would always peg low at the start of the test. It's seeing the capacitive charge. And then very quickly that would charge up. And then the pointer would start rising back up to the high end. So capacitance starts high, goes to zero, and does it relatively quickly. Absorption, it does essentially the same thing, but with a lot more time involved because the absorption is occurring in the insulating material. It will polarize, and it's, of course, not a good conductor. Insulation is not a good conductor for obvious reasons, and so this takes more time. And this is why your readings can change over 10 minutes or 15 minutes or even longer. But your leakage current is the one you're really worried about. That's what's getting through the insulation and going to ground. And that behaves differently. That charges up very quickly to a level that's commensurate with the applied voltage, and then it will stay that way. And if you note over on the right side of the display, eventually the charging currents drop out and all you're seeing is leakage current. But the problem with that is with big equipment, that can take a long time. So we're going to kind of address that this morning or this afternoon. Next. This is another depiction. Leakage current is primarily resistive. Capacitive current, it's just capacitance to charge right up. And absorption is a combination of the two and is so a little bit harder to deal with. Next. This is just another portrayal. Remember, you have dipoles, you have charges in your insulating material. And without in its just normal operating state, that charge is random. But when you apply the DC voltage across it, you're now polarizing it. The positive ends of the molecules try to turn towards the negative plate and vice versa. And so as these large molecules, as they adapt themselves and orient towards the charge, then charge is moving and current is a movement of charge. So that is your current. That is your charging current. And over the billions of molecules, I guess, that there are in a large piece of equipment, that adds up, and that becomes significant. So next. So these are your three currents, and these are going to affect what you see in your test, and we're going to talk about then how you deal with them in the various tests. And note that the main thing is depolymerization. As insulation degrades, those molecules break down, and so that's depolymerization, because normally in brand new insulation there's huge polymers, and as the linkage breaks down, the insulating material becomes more polar, and then that promotes breakdown of the material. Next. And two big factors, insulation testing is time dependent, and it's also temperature dependent. And so keep that in mind, and we're going to come back to that, and we're going to talk about that time and again. But those are variables that you need to take into consideration when you're doing an insulation test, and especially when you're keeping records or when you're reporting the results to a third party. Next. Okay, we'll start with the short time or spot reading test. This is the easiest one to do. This is hook up and take a reading. This is what you're doing when you're just doing your go no go type testing. But with long-term testing, then this can become a little bit hard to deal with. Doesn't give you sufficient information sometimes, and it is highly temperature dependent. Next. So this is what you'll be seeing with a typical spot reading test. Your readings are rising with time because your charging currents are going to zero, so your readings are going up. But note that if somebody took a reading at 30 seconds, they get a significantly different reading than would be attained at 60 seconds. And so without that information, you can have confusion when you're trying to compare different tests. So always keep your time in mind and report that if you're reporting your test result, how long it took you before you took the test. Next. So this is a good reading for small equipment because it comes to charging relatively quickly, and so it may give you more information on small equipment. But on large equipment, we're going to look at how our testing procedures take advantage and try to deal with that issue. Next. Okay, this is a good representation of the time factor and the record keeping factor. You can have what is called distributed leakage, which is represented on the lower line here. That's where the leakage is flowing pretty much uniformly based on the structure of the insulating material. And so that may give you a comparatively low reading. Now, we're not talking about readings that are down around the failure point. We're talking about readings that are acceptable, but not way up in the high range, but they're holding constant over time because you just have distributive leakage. There's no problem spot that's developing like a burn track or a tree or something like that. And so if you see readings holding steady like that, even though they're not real high, you don't have to worry about apparatus B. That's in pretty good shape. But look at apparatus A. That's giving you very good readings. It's up in the high gig ohm range, but they're changing relatively rapidly. So that's a piece of equipment that you actually want to be concerned with. It could be getting moisture ingress. It could be a piece of equipment in a factory procedure, for instance, and there's a lot of moisture nearby, and maybe you need to put up a moisture shield or something like that and stop that progressive deterioration. Next. Okay, so next we'll take a look at time resistance methods. And in this case, you're comparing readings at two different time signatures and you're looking for change. So you're getting around the limitations of just taking a single spot reading and then having to look at the number you got on your display and make a decision based on that. These tests help you to make that decision. Next. So with time resistance test, your polarization, those effects hold your readings down to relatively flat. Over time, readings that stay relatively constant are based on leakage because leakage is relatively constant against the applied voltage. And so we're trying to use this technique to separate readings that are based on primarily on leakage from readings that are based on the charging currents, which are fairly constant and not really a problem. Next. So here's a graphic example. The bottom line is equipment that is in relatively poor condition, has a lot of leakage pads in it, and it holds the reading down. So you get a relatively flat line like that. That regardless of what the reading is, that's telling you that leakage is fairly prominent, and you might want to take this offline and dry it out, clean it up, whatever, do some preventive maintenance. The top line, you don't worry about it because it's rising nicely, and that's mainly there. What you're seeing are charging currents, which are not really a problem. Next. And so the kind of like the basic time resistance test is your PI, your polarization index. This has been around almost since day one. This is comparing a 1 minute reading to a 10-minute reading. And I have a feeling that as we go along, the newer materials have shorter time signatures. They come to full charge more quickly than the older materials that were around in the last century. And so I think PI may gradually fade in significance, but it's still largely used to a great extent, and it's still very important, and it's still very effective. Next. So here we see typical readings from a PI. So if you're getting a reading that's up over 4, that means that you don't have very much leakage current. Your tester is seeing mostly charging current, and so you're in pretty good shape. Readings that are up over 2, not really a problem. You may want to look at them, in 6 months or whatever. Not really anything to worry about. But readings that are down around 1, there you're getting a lot of leakage current, and that equipment may be getting ready to break down. So that's the stuff you want to schedule for maintenance. Next. Now, here's an example of large equipment that has a lot of charging. And this is a good example of why PI can be a very effective test for you, especially if you're on very large equipment, you're in a gen station or something like that, and it can take an hour for a big generator, for instance, to charge up to full charge and give you your final reading. It gets like a clock hand. You can't see it moving in front of your eyes, but walk away, do something else, and come back, and you'll note your readings have crept up higher. But you don't necessarily need to be all the way up on that high end, and you certainly don't have the time in your work schedule to take an hour. So instead, the PI, 10 minutes, it's looking at how the readings are changing, and it's looking at why the readings are changing. And so you can make a decision based on that and not spend so much time doing testing. Next. Now, those are your time-dependent tests. Now we'll take a look at another test, which is step voltage. And here, instead of looking at time with a single test voltage, we're now going to change the voltage and see what effect that has. And next. Okay, with a step voltage test, now you can design your own based on what your equipment can do. But the industry standard is to increase your voltage every minute for 5 minutes. And equipment that's set up to do step voltage test automatically will simply ask you, what is the limit? How many volts do you want to go up to? So you tell the equipment 1 kV, and so then it will automatically divide it 200, 400, etc. And it'll run the initial voltage for 5 minutes, and then it'll ramp it up to the next higher voltage. So let's say 200 to 400, for instance, and run that for a minute, and so forth. And it'll do that for 5 minutes, and it'll save all that data. That's your standard step voltage test. Next. And what the step voltage is doing, good insulation should be able, like the top line, should be able to stand up to increases in voltage. Now, especially if you're working with sensitive equipment, you may want to look at the specs and make sure that it can, it's designed to withstand the top voltage that you're going to. But most common equipment running off of, line voltages can take considerable increase in voltage because you have spikes and things like that that routinely come down through the utility. And you can't have your equipment burning out every time there's a lightning strike somewhere. So you should get a line that looks like the top where it stays relatively flat. If you see something like the bottom line where every time you've increased the voltage, you get a substantial decrease in your insulation values, then that's telling you, okay, there's problems here. And this is particularly good for old, dry, brittle insulation like you get sometimes in motor windings. If you do a spot reading test, that insulation doesn't have a lot of moisture. It may give you a really good spot reading test, but you put a step voltage test on it, and now every time you increase that voltage, the cracks that have developed in that insulation, more voltage pulls leakage through more cracks, and your value drops. And so you can really spot in things like motor windings. A step voltage test will give you a good way of recognizing these impending problems that may soon be breakdown. Next. Okay, now this gets a little dicey here. Now we're going to go to dielectric discharge test. And I have to kind of skim through this because it's fairly complex, but we've been looking at so far at polarization currents and what they can tell you, and you can get a lot of effective information out of that. Dielectric discharge uses the reverse and looks at depolarization or discharge of your stored charge on your equipment. Next. So the problem with looking at polarization current is, of course, what we've been referring to. It's dependent on other factors that you have to deal with, particularly the added effect of charging currents. So now we're going to look at discharge, which eliminates the effective charging current and just looks at what happens when the charged equipment is now discharging. So next. Okay, so now we've charged up your current and your test item, and we're going to cease the test voltage. We're going to not apply any more test voltage. Your dielectric discharge test runs for 30 minutes, so you get full charge. And so we're going to stop that. And now we're going to see what happens next. Okay, so now we're going to discharge the test item. We're going to see what stored current is still left on the test item and what happens to it. Next. Okay, this is called reabsorption or relaxation current. So it's the reverse of your charging currents. Okay, next. Okay, you can go to the next one. And typically what happens is a dielectric discharge test waits a minute so that the capacitive current will be gone. That drops quickly. And now it's only looking at the stored current in the insulating material. Okay, next. And now it's going to measure how much current is still left discharging after a minute. Next. And a high reabsorption current, that indicates that there are problems with depolymerization in the material. It has a lot of polar molecules because the material is breaking down. Next. And so the tester does a relatively complicated calculation, and it posts up on the display a figure of merit, just like a polarization index does. Next. And this is the calculation that your tester will do. And okay, you can, with a fairly good tester, you could probably do this manually, but that's kind of tough. So it's a good idea to have a tester that has the dielectric discharge built into it, and then it will do this calculation for you, and it will post a number up on your display. And that's a figure of merit. It's free of units of measure. Okay, next. And so let's see what. Okay, so basically, I think I pretty much covered what we're looking for here. So okay, next. Okay, so what we're looking for here is a low number indicates that there was relatively little reabsorption current, meaning relatively little dispersal of charge. A high number indicates that there was a lot of charge in the material, and so therefore that indicates a potential problem. Next. So this is a typical DD result, and note this is the reverse of polarization index. Polarization index, high numbers good, low numbers bad. With dielectric discharge, it's the reverse, and a perfect insulation will typically give you a 1. And as the numbers deviate from that, it indicates more and more depolymerization of your material. Next. Okay, ramped voltage. Now this one I had to skim over. This could take an entire presentation all on its own. But what we looked at with the step voltage test, the ramp voltage is a refinement of the step voltage, where now you're going. This is built into your tester. If you have a relatively sophisticated tester that has a ramp test in it, you hit the button, and what happens is it starts to apply the voltage 1 volt at a time. And so it will creep up 1 volt at a time, and it will store the reading at every voltage up to the top voltage that you selected. Okay, next. And this is a pretty sophisticated test, and you really, before you apply this, you really should read some literature on it, and I can provide you with that. I have a couple articles, so let me know if you're interested. It's more sophisticated than a step voltage because you can actually get information out of it regarding the actual nature and of the problem in your insulation and where it may be. Next. Okay, so I think I pretty much covered this. That basically compares what you see with your step voltage versus your ramp voltage. Okay, next. And so what we're looking for then is a smooth curve. And a tester that has this test built into it, then of course, will send all the information uh, to your uh, to your storage device, and you can download it, and print it on your computer, and you can look at the graph and see what information you can get off of that. So you're looking for a smooth curve, and deviations from a smooth curve tell you something about what the problem is in your insulation. Next. And you can also, you watch the voltage and progress of the test on the display, because it will show you the line creeping up, and you can actually do something that's similar to a tip-up test, where what you're basically looking at is the current should follow your voltage, and if it doesn't, then the current will start to creep up higher than the commensurate voltage, starts to deviate from what you would expect from Ohm's law. And so let's look at the next slide. And what you'll see is something like this. The line you want to see would just be a straight, uh, consistent rising curve. But now you start to see the current depart from the voltage. That's impending breakdown. So that's where the problems with your insulation is allowing too much current to go through the ground, and it's getting ready to break down. And so this is a good time then to terminate the test. And if you look at your curve and the test results, you can get an idea, if you're familiar with all the the particulars of this kind of test. And like I said, it's available in the literature, and you can get an idea where the problem is in your insulation, and what you might have to specifically deal with. Next. Okay, so this is just a summarization then. This is the idea of how you have all these different tests. You don't necessarily have to do them all. You can design or plan your test procedure for things that you've been seeing with your equipment, or you may suspect a problem and you may want to explore that. And this is just a review of how the different tests look at your equipment in different ways, and can recognize impending problems. Next. Okay, so in the last few minutes, we're going to do a quick review of the properties of an insulation tester and what you might want to look for. So we'll look at guard terminal first. This is an example of a two-terminal test setup where the industry standard is negative to circuitry and positive to return. And in this here, we're looking at phase A, for instance, and how it relates to all your other phases and ground. Next. So now we've engaged the guard terminal, and in this case, we're looking at one phase to ground, but we've guarded out the leakage current that's flowing on the surface, because you may not be concerned with that. You want to take it out of your measurement. You want to see how much is getting through your insulation. Next. This is just a couple quick looks at different types of setups using a guard terminal. Here we've guarded out bushing 2, and we're just looking at bushing 1 to ground. Next. Okay, so these are things to think about then when you're purchasing an insulation tester. If you're only going to do spot go no go type testing to make it to reach a standard or to spot a piece of equipment that's shorted out, then you don't need a whole lot of complication and a whole lot of extra features on your tester. But on the other hand, if you are going into more sophisticated testing, then you want to, and you're purchasing a tester, then there's various things that you want to look at and make sure that they're in line with your needs. Next. And so these are quick review of some of the things that we're going to touch on quickly and indicate their significance. Next. Okay, leads. Now, these are very often overlooked because they're, you kind of take them for granted. Make sure that you're using a lead set that's commensurate with what you're trying to do. And especially with if you're using a tester that runs very high up into the teraohm range, you need a very good lead set. You can't have crosstalk between the leads. You may be able to get away with that if you're only measuring in megohms, but if you're going up into high range, then you want to have a set of leads that don't talk to each other. So if you can hold the leads together in your hand and your reading up on your display is changing, that's no good. If you can move the leads and the reading is changing, that's no good. You want to have a good set of leads that's isolated from all of those extraneous concerns. Next. And we just indicate, especially on high range measurements, you want to do things. Sometimes you want to, for instance, suspend your leads in air instead of having them lie on surface because you can get tracking. So that's just some points on the effective use of your lead set. Next. And accuracy. Okay. Watch your accuracy statement of your equipment. This kind of pertains more to the old analog units more than it does now. But look, for instance, for percent of reading, not full scale. That's deceptive. You want to have the same accuracy at every reading, not just at the high end, because your full scale accuracy on a logarithmic scale will change as it goes down the scale. So that really is not something that you want to have for top quality assurance in your reading. So you want the same accuracy at every reading. And also look for the number of digits at the end of the reading. Sometimes they'll all vary a little bit, but a good quality tester, it's usually about 2 digits. Poor quality testers, you might see 8 digits. So that can add up to a lot of variance in your reading. Okay, next. Now, voltage delivery. We'll talk about this. Load curves are important. You may want to look or ask to see a load curve for the tester that you intend to buy. Next. This is what you want. You want your voltage, your test voltage, to rise sharply up to the selected value. So, and this should be commensurate pretty much with what they call the 1 megohm rule, which is that you never want to see less than 1 megohm. That on your equipment, that generally is indicating that there's a real problem. So once you get above a megohm, or sometimes it's a little bit higher for equipment that's higher rated, but you want to follow basically the 1 megohm rule. So once you get up to a megohm, you want to have full voltage. Below that, then your equipment may be getting ready to break down. So then your voltage can decay, and that's fine. But let's look at the next slide. This is poorly designed equipment where your voltage rise is not sharp. It's just very slow voltage rise. So, okay, yeah, eventually it gets to 5,000 volts. So the manufacturer will say this is a 5 kV instrument. Yeah, fine, it is. It'll get there eventually. But with a slow voltage rise, note that it's not giving you selected voltage over the low end of the scale, which is the most important range. That's where you're making your determination of what to do, take it out of service or not. So if you're trying to do a 5 kV test, you don't want 3 kV at, let's say 100 megohms or something like that. So that's what your load curve shows you, and that's a good thing to examine before you make a purchase. Next. And noise. Okay, just tailor that to your environment. Look for your noise protection on the tester, because if you're going into something like the substation, then you want very high maximum noise protection, and you might want to pay the extra money to get that. So just, tailor your instrument to your environment. Next. Guard terminal, we talked about that. Guard terminal, this is one of the areas where a poorly designed tester that's trying to go to market on a low price, one thing that the engineering can cut is your guard terminal quality. They can say, oh yeah, we have a guard terminal. But remember, when you engage the guard terminal, it has a plus minus accuracy just like your plus and minus terminals do, but that accuracy is added on to your basic accuracy. So you now have an additional uh, plus minus rating added on. So you want that to be around maybe 2% or something, where it's not contributing a lot of additional inaccuracy to your reading. Poorly designed guard terminals can contribute immensely to the degradation of your reading. So just be careful to look into what your guard terminal error is before you make a purchase. And next, and we'll take a look at you can do the arithmetic on here, but this can show you how much your guard terminal can contribute to degrading your reading. So that's why you want to have minimal guard terminal error. Next. Okay, and I think this is our last consideration, and we can go to questions. IP rating should be available on the spec sheet. This refers to how well your instrument casework can stand up to the environment. So your IP rating is something like 5.4. The first number indicates protection against dust, and if you're working in a mine, forget about it. Uh, the dust in that kind of atmosphere can take your equipment out of service sometimes in a matter of months, because all of that will get inside the equipment and degrade the circuitry. The second number has to do with moisture. So if you're in an environment where there's a lot of moisture spray and things like that, you want to have maximum IP rating. So look at your IP rating. The higher the numbers, the better. If you have a low IP, you can't take that into any kind of a demanding physical environment. Okay, next. And the last thing is the IEEE 4300, 43 rather, that was revised in the year 2000. And that has a bearing on rotating equipment, but remember, insulation is insulation. So rotating equipment is not a whole lot different than other types of equipment like cable, for instance. And so a lot of the same ideas uh, pertain or apply. And that standard, what it basically said was for very high uh, operating voltage equipment, We don't demand that you have very high uh, output voltages on your testers. 12 kV is enough. If you're testing 60 kV equipment, you don't have a 60 kV tester because it's impractical. With brutally expensive, large equipment, you don't need it. The IEEE standard said 12 kV is enough and you can test anything. Okay, with that, I think that brings our webinar to a conclusion as far as the presentation is concerned. And now we can go to questions. And I thank you for your attention and your attendance.
Okay, guys, so that's the end of the presentation. So if you have any questions, you can write it down in the chat box and we'll try to answer it for you. And before doing that, I would like to remind you that there will be a pop-up screen when you close this webinar box. Please answer that survey form that is for improvement or future webinars. At the moment, we don't have questions, so maybe we can give at least 1 minute or 2 minutes for you to type in the questions you may have. And also, for any further questions, you can also send us an email, and we'll answer it through email as well.
Okay, thank you, Michael. I think we don't have any more questions now. But if you have any query inquiries, please send email to our Mega Hong Kong mailbox, which you can see in the chat box. As a reminder, if you are leaving, please help to fill in the survey for improvement. So if there's no any other questions, we'll end the webinar here. Thank you, Michael. Thank you, everyone, for attending, and we hope to see you again next time. Bye-bye.